Cool. I think we are good to go. So, hello, everyone. It is great to see you all. And it's such a delight to welcome Shami Tsai here, who joins us today to continue our Rocky Worlds discussion series. Before we start, just a quick reminder of the netiquette. Please use your full name on Zoom and please stay muted throughout the talk. At the very end, we will have time for questions and discussion. If you would like to ask a question, that would be great. Please do turn on your video if that is possible so that we can see you. And now, without further ado, I will hand over to Shami to talk to us about probing sub-Neptune interiors through their atmospheres, the case of K218b. So I will stop sharing screen and let you take over.
Thank you so much, Anjali, and thanks for having me. Let me share my screen. So I have two screens. I'm not sure if I'm showing, are you seeing my main screen or seeing the
We're seeing the slide, it's perfect.
Okay, so just one slide. Okay. All right, so I like to show you, I like to start by showing you this timeline for visualizing how far we have achieved as an exoplanet community. So over the 3 decades, we started from not knowing any extrasolar planets to now we have more than 6,000 or so confirmed exoplanets. And here I listed in the upper panels where I labeled planet hunters. So we have used the radial velocity and transit methods to detect new planets. So especially the Kepler mission using the transit method allowed us to study planets at population level. And I also think this is a really exciting time to study exoplanets because we are shifting from the era of finding new planets to be able to study them in more details to characterize them. And this is thanks to the development of more precise spectroscopies and new space missions. I've also selected a few milestones listed here. So starting from, we first detected the first exoplanets around the Sun-like star, to the first hints of an exoplanet atmosphere by detecting the sodium doublets, and to now with the JWSTs opening the infrared spectral window, being able to detect gas molecules such as carbon dioxide and sulfur molecules. I don't think this audience needs this introduction, but for the context, spectroscopy is really a powerful tool. And when the planet is transiting, if it has an atmosphere, because different molecules in the atmosphere have distinct absorptions due to their electronic transitions, they will cast different transit depth at different wavelengths. And this is how we can infer different atmosphere composition and characterize their atmospheres. So the wavelength coverage and resolution do matter for spectroscopy, and they matter a lot. So this is just to demonstrate for a gas giant. Before the JWST era, this is in this infrared wavelength coverage, we have two broadband observations from the Spitzer, and now with the JWST, this is using near spec G395H, shown at Alderson et al. You can see with the high resolution and precision, we can confidently identify different molecules such as water, CO2. And one of the most striking results from Kepler is that the majority of planets we have found are smaller than Neptune. Now we look at these planet occurrence rates around FGK stars from Fulton and Pettigrew et al., showing the number of planets as a function of planet size and separated by a gap separating these two populations. And we are able to identify this gap due to the improvement of Keck and Gaia's better constraining the stellar radius and therefore the planet's radius to about 5%. So the population, the smaller population below the radius gap, they are consistent with rocky interior, and whereas the population above the gap, they require extended hydrogen-helium envelope to explain their sizes. And one of the leading explanation is, this is based on Occam's razor's principle, is they share the same, these two populations share the same origin. They are all born with a rocky core with accreted hydrogen primordial gas from the disk, but some of them have lost their atmospheres and become this rocky population. So this has been predicted by, this is one of the rare examples that models has predicted this bimodal distribution of the radius. And on the right, I'm showing the Maslow's timescale due to energy limited escape as a function of envelope mass fraction. So I don't know if you can see my cursor. So at this point, this is where the atmospheric mass is at 1%, 1% of mass. And this turns out to be the most stable state for these small planets, because if you have more massive envelopes, at this 1% mass, and it starts to double your planet's radius. And if you have more envelope, you start to increase your planetary size. And because the energy limited Maslow's rate scales with radius to the power of 3, the increasing mass loss will quickly decrease your Maslow's timescale. And if you lose more atmospheres, because your size is basically determined by your core size, the less atmosphere you have, the faster you're losing your atmosphere. So this is the most stable position, which can be understood by this cartoon. And this 1% of mass corresponds to this around 2 Earth radii, center around 2 Earth radii Sub-Neptune population. And what's more interesting is the position of this gap is a function of core density based on this photoevaporation explanation. So the closer the planets, the denser the core, the planets needs to be closer to lose their atmosphere. So on the right plot, if you have a higher density of core, the gap will shift it toward the star. Whereas you have a lower density, it will move away from the star. So this is the first level of constraints of the interior we can get by purely using planetary size distribution. And an alternative view of this planetary radius gap is instead of born with the same population and through evolution, some planets could form beyond the water slope line of the disk, and they could have different, they can accrete different materials and have different bulk density. So the distribution I showed before are for sun-like stars. So here on the left plot by Luck and Pell in 2022, they look into a small sample of planets around M stars and found where the planets are rare for FGK stars, the gap doesn't seem to be so obvious for M stars. So instead, there are still quite some planets populating around this gap. And if you follow this blue curve, and that's when you assume if the interior has 50% of water, and that could explain many of the planets in this population. So they provide a different perspective. Instead of a radius valley that's separating the two populations, the separation in terms of density is more clear for separating these two populations. And this is also confirmed with formation studies showing that for smaller mass stars like M stars, they have lower planetary mass to trigger type 1 migration, which can populate more water-rich planets in this gap area. But there are a few challenges for this water-rich planet story. So one of the challenges is water may not remain as an isolated layer in the interior. So in this study by Dorn Lichtenberg, they show that when water partitioned into the interior, they can significantly reduce the radius if it goes into the interior. So it cannot it may not provide satisfying explanations for the larger radii. So all in all, these population has a well-recognized degenerate problem. So only based on the measured radius and mass, you can imagine you can have different core density and with different mass fraction of the envelope to achieve the same bulk density. So one way to break this degeneracy is by observing the atmosphere composition. So this is experience learned from our solar systems. Some of the species could be dependent on the mass fraction of the atmosphere. So for example, ammonia is abundant on Jupiter, but it's depleted on Titan because it lacks of the deep reservoir that recycling nitrogen. So we perform the same exercise for a Sub-Neptune under Sub-Neptune conditions. So ammonia can maintain a high abundance, but if there's a small atmosphere, when you place a 1 bar surface there, it will lose ammonia very quickly over a time scale that's shorter than the geological time scale. So ammonia, as an example, is a tracer to provide hints about the atmosphere mass fraction. But I call this a false negative for ammonia because when you have no detection of ammonia, it could also be due to dissolution into the interface between the atmosphere and the interior, whether this interface is liquid water, or in this case, I'm showing the study by Schroeder et al. If it's a reduced condition of magma oceans, nitrogen is very soluble, so it can also dissolve ammonia. And a idea that has been around these years is that the coupling between the interior and the atmosphere, when the silicate interior at the high temperature and pressure conditions and they are molten, you would have coupling between the interior and the atmosphere, and this saline SiH4, which is an analogous analogous molecule for methane, can potentially probe this fully molten silicate interior and the envelope if the magma ocean has a reduced condition so that most of the silicate can bond with hydrogen and instead of existing in the SiO form. But the challenge is if your atmosphere has a high metallicity from pebble accretion, which is could be the case for many sub-Neptunes, you would have methane competing with saline at these high metallicity conditions. So next, I'll take a deeper look at a population of temperate sub-Neptunes and using a K218b system as a case study. So K218b is definitely a very popular exoplanet. It's a Sub-Neptune within the habitable zone of its host M star. It received about the same stellar radiation as our Earth receiving from the sun. So as we will discuss, the equilibrium temperature does not really provide sufficient information to determine whether the planet is habitable, even though the planet is within the stellar habitable zone. So here's the origin. It has a very interesting origin story of this planet. The previous Hubble and Spitzer data showed H2O vapor indicated in this transmission spectrum. But within this wavelength range, the absorption of water is degenerate with methane. So this is argued by the study of Bazar et al., showing that methane also provides an equally good fit as water, but because it has more spectral lines with this WC3 window, it should dominate this wavelength range. So in other words, if water and methane have similar abundances, methane will contribute to the absorption in this wavelength range. And if we can observe a wider wavelength range, we can break this degeneracy. And this is exactly what JWST does. So about 2 years ago, JWST observed this planet in transit with near-res and near-spect. So you can see now the features are much better explained by methane. And in fact, this is, if I remember correctly, the first targets with both CO2 and CH4 detections. And due to from the detection of both molecules, CH4 and CO2, as well as non-detection of ammonia, the team led by Madhusudan preferred an explanation of a ocean planet under a thin hydrogen atmosphere, dubbed as Haitian planet for this planet's K218b. The reasoning is that if there's an ocean, the ocean can act as a carbon reservoir and in equilibrium with the atmosphere, providing CO2. And as we have discussed, if it has a thick atmosphere like a Sub-Neptune, ammonia should be observable. However, with the analysis, with the analysis using photochemical model in Morgan et al., they show that methane is actually unstable if you have a Haitian, under Haitian conditions with a thin atmosphere. So the first panel shows the lack of methane if you simply have a thin atmosphere. So you need a source to resupply methane in order to battle against the photochemical destruction of methane. And you can either have methanogenic flux from biology, or you could, if the planet is a Sub-Neptune and the deep atmosphere provides fast chemical recycling that can provide methane into the photosphere. And the authors favor the Occam's razor's answer with the thick atmospheres. And in the same study, the author also reported a tentative hint of a molecule, dimethyl sulfide or DMS. And this sparkled a high interest because this molecule is primarily made by microbes, phytoplanktons in our oceans on Earth. So on Earth, this molecule has a very short time scale, though. The time scale is about 1 day because when it's emitted to the atmosphere, it's quickly being destroyed by our solar UV radiation. But this is a different planetary conditions. So with JWST, we are starting to probing biosignatures, potential biosignatures under agnostic conditions, because the current spectral windows don't allow us to have access to oxygen-based gases yet. So in a study we did in 2024, we asked 2 questions. Can DMS actually accumulate to detectable level if it's a hypothetical Hessian world? And if so, what's the observing window to see them? So we applied modern Earth's biological flux in our Hessian photochemical model. And here is the summary of the various abundances. So the main takeaway is if you just look at the blue circles, so it takes about 20 times Earth's biological flux. So X is the flux relative to modern Earth's value. So it takes about 20 times to reproduce detectable DMS level. So current modern Earth biological flux cannot reproduce detectable level of DMS, but enhanced production can make DMS reaching higher levels due to self-shielding effects. And in this state, it also accompanied some organic hazes and sulfur hazes. But we have also argued that the detection across the 3 to 4 micron region for both methane and DMS seem to be inconsistent because their opacities overlap in this wavelength range where they have the same fundamental CH stretching mode. So you can see from this opacities shown on the right. So methane is in blue where DMS is in green. So in our test spectra, when we include the detectable DMS, it only shows a small difference of about 10 ppm in the transit depth, which is smaller than the observing uncertainty. So it's hard to distinguish methane signal just from this wavelength range. Oh, sorry, I mean DMS signal. And an even more extended view of how list of hydrocarbons share this CH stretching band is beautifully illustrated in this plot by Nirala et al. So these are all organic molecules, and especially where I highlight the methyl group, that's where you all have this CH stretching mode. So I think this is where we have reached the limiting capacity of JWST resolution to distinguish different organic molecules. But in the infrared, for this case, we show that the byproducts of DMS have wider features across 9 to 11 microns. And if DMS is really present, there should be a more indicative spectral features for this Hessian world. And this is exactly what Miri reported in this paper by Malustan et al. 2025. So this is the Miri spectra with 1 transit, and they reported the features can be contributed to either DMS and or DMDS, which is a byproduct of the same biosulfur gas. But before we go into a detailed analysis, there's something off about this report. So if you look at the spectral feature, it's about 0.02 transit depth variation. This is about twice of model assuming habitable surface temperatures would predict. The spectral variation is double that. And they also retrieved the photosphere temperature at 1 millibar of above 400 Kelvin. So which seems to be a hint that your spectral signals are still dominated by noise. So there are a few questions. First is, does the spectrum really show molecular features? And a research note released soon after the paper led by Jake Taylor, showing that the data actually favors a flat line rather than a spectral with molecular features. And there are also several follow-up studies showing that these if there are molecular features, they are not actually associated with DMS. So a paper by Louise Wilbanks, they show that the Bayesian model comparisons does not directly translate to molecular detection. So they searched the HyTran database of several molecules and argue that there are other molecules that can provide equal Bayesian evidence. And similar studies was also performed by Raphael Locke, and they jointly analysis previous near-res and near-spec spectra and have similar conclusions. And this paper by Kevin Stevenson also showed that the MIRI data could still have MIRI systematics, and it can be it's sensitive to the binning choices. Okay, but so far there hasn't been a study addressing if the retrieved abundances make sense in terms of our knowledge of physics and chemistry. So this motivates us to do a further revisit study. So in this table, I compile all the retrieved abundances, all the observational constraints we gather so far. So the main summary is we have robust detection of methane and CO2 with the abundance of around a few percent of methane and larger uncertainties of CO2. We have no detections of ammonia and water, only upper limits, 2 sigma upper limits, about 1% and 10 to the minus 3 for ammonia. The DMS has only been reported in Madhusudan et al. And hasn't been confirmed by other independent analysis. And instead, they argued the feature can equally be fit by other organic molecules. So we are trying to address 3 questions. And the first is, how do we physically explain the observed low water abundance? And does the retrieved atmospheric composition make sense physically and chemically? And we are for border populations of these temperate sub-Neptunes, what can we learn about their interiors by examining if their atmospheric composition is mutually consistent under different conditions? So first questions, previously, there's a common statement saying the reason for not seeing water in K218b's transmission spectrum is because water condensed out when you form water clouds. This is a reasonable statement, but the real question is, does it really provide, how does it provide the thermal conditions to rain out water. So all the previous studies all artificially reduce the incoming radiation by 30%, motivated by a similar bound albedo of Earth. But I should highlight that this bound albedo should be a diagnostic outcome. If you are doing a 1D climate modeling, this directly removing stellar flux at the top of your atmosphere has two artifacts. So you artificially remove energy that would have been absorbed by the atmospheres otherwise. And some irradiation will be radially scattered, and that will additionally contribute to the bound albedo in your model. And then there's another alternative explanation. If the planet is carbon rich, it could also lower the water abundance. But in our analysis, we quickly found out if by the time that water is dropped below the upper limit, you very quickly lose your CO2. So if CO2 is also seen, you cannot explain the low water abundance by a high carbon content. So instead, from the HARPS and Carmen's high-resolution RV data, this analysis in Sarkis et al., they show that K218b actually has an eccentricity of about 0.2. And the study running the evolution of tidal interaction of the inner planet K218c further shows that if the inner planet is a gaseous planet, it is possible that because of the slower deformation timescale, it is possible that the tidal damping is not sufficient to circularize K218b within the system's time. So in this study, we applied the orbital eccentricity of 0.2 to explore whether this can physically explain the water condensation. So here, on the left is the temperature profiles at apoastron of the planet. And if we further include water condense, that's the solid line, the temperature below the water clouds decreases a little bit. So the water starts to be more efficiently condensing out, as shown on the right. So going from the dashed line to the solid line is when the radiative effects of water cloud is included. So the water above the co-trapped is about 10 to the minus 4, which is consistent with multiple retrieval constraints. So we perform 1D radiative calculations at different orbital distance. So here is from left to right is from far from the star to closer to the star. So if you go from left, that's a cold star scenario when the planet is just moving out of apoastron. As the temperature increases, you're entering this shaded region is where you interestingly have two stable states. So if you start with water clouds, the scattering effects of water clouds will remain, the atmosphere will remain cloudy. But if you start with a cloud-free scenario, your atmosphere will also stay cloud-free. So the whether the observable, whether the photosphere water is depending on the mixing timescale, which is about 1 month, which is comparable or longer than the orbital period of K218b. So we argue that at least for most of the orbits, the water should be condensed out. So we recognize the radiative effects of water clouds are intrinsically 3D, but our idealized 1D model still qualitatively capture this bifurcation behavior due to the scattering of clouds. And next, we are testing if the retrieved abundances are mutually consistent. So what we are doing is we impose observational constraints, which are the detect methane and CO2, and we put in our photochemical model to see if it's consistent under the Haitian or Sub-Neptune scenarios. And we also further test if we fix the reported DMS abundance, what would we see if the DMS is actually present when we're being agnostic. And we run this with our updated sulfur chemistry, including a paramolecule that could produce CS2. So for a Haitian scenario, what we immediately found is high methane efficiently produced hydrocarbons. So on the right, you're seeing all the three lines overlap each other, and these are ethane, CO, and propane. That's C3H4. All reach about 0.1 above 0.1%. If we further fixed DMS at the reported value, we further have more abundant of CS2. And this is because when DMS is dissociated, it makes CH3 radical, which can combine to form this molecule, paramolecule of CS and CS2, which have prominent spectral features in the infrared. And on the other hand, under Sub-Neptune conditions, the hydrocarbon production is confined at high altitudes at low pressures. And when we prescribed a DMS profile from the reported value, it marginally increased CH3SH and DMDS, while other hydrocarbons almost did not change. So we summarize the when we input methane and carbon dioxide, and we summarize how our models produce different gases. And the point of doing this exercise is we identify several diagnostics. So C2H6 should follow methane, and so does propane and C6H6. So if I list different scenarios here, we have Sub-Neptune and Haitian, and Sub-Neptune could potentially host a molten magma ocean surface, and Haitian could potentially have DMS. So we can use these different molecules to distinguish different scenarios. So for example, the C2H6 follows methane. So the ratio between C2H6 and CH4 is much higher for the Haitian scenarios, regardless of the presence of DMS than the Sub-Neptune scenarios. And if we can detect CS2, we can further test whether biosulfur gases are present. So for the detectability of C2H6, we did a quick test. So this is in the MIRI. If we have 3 transits, that's the green dots with arrow bars, showing that we could potentially differentiate these 2 Haitian and Sub-Neptune scenarios. All right, so for the 3 questions, we found that water clouds driven by orbital eccentricity could physically explain the low water abundance being co-trapped. And the detection of methane, but no detection of other hydrocarbons seem to be inconsistent with the hydrogen scenario. With multiple transits, more mirror data, we can get more insights into the temperate Sub-Neptune interiors. We have also presented whether DMS is possibly produced by abiotic process without life, and also new cross-section measurements in the paper. So if you're interested, welcome to check out the paper on the archive. I'll stop here and happy to discuss with you.
Thank you so much, Shami. And we have plenty of time for questions and discussion. Would anyone like to get us started? Feel free to either raise your hand or you can also put questions in the chat. Just a reminder as well, if you would like to ask your question, please do turn on your video if that's possible when you ask it as well. I don't see any hands so far, so maybe while people are thinking, I'll get us started. I think it's really exciting that we're seeing this regime now where like the hydrocarbon chemistry is really being probed. And I guess the longer the hydrocarbon chains, the more complex it is to model that chemistry. Could you comment on should we be expecting even larger molecules than C6H6, I think was one of the larger ones I saw in your slides? And how challenging is that to model? Is that something that is something that will be important for the future?
Yeah, absolutely. So the chemical networks are incomplete for high number carbon species. This is a well-known, well-recognized challenges in modeling the atmosphere chemistry. So the model we are using have hydrocarbons with carbon number higher than 2, but that is for completeness for better predicting C2 species. So even the C6H6, I will treat it as a proxy for haze precursors because the pathways for producing benzene and for destroying benzene are not complete. But we can still learn something, as in we should treat it, we can treat it as a proxy that in reality that would likely lead to production of larger organic molecules and potentially hazes.
Very cool. Do you think there's scope to, I guess it's difficult to start to distinguish some of these really long chain things if they have similar functional groups. But are there any features that you think will start to identify the larger, maybe similar to the haze, like Tholen features that we expect?
Yeah, I think I have a slide I didn't show. So here are some of the stable hydrocarbons. So those are with even number of hydrogens. So C2H2, C2H4, and C2H6. While they share some of the stretching modes around 3.3 microns I mentioned, they do have different features. We can distinguish them in spectroscopy. So for example, the orange one is C2H2. There's a feature around 3 micron, and that's not overlapped with other molecules. And for C2H6, it has stronger feature in the mid-infrared. So this is the so you start from 6 to 8, 9 micron. And here I have two C2H6 lines here, and that's because the earlier hydrogen database doesn't include some of the overtones of C2H6, so it only has this narrow absorption. So there are still some incompleteness we should gather for some of these molecules like C2H6. But nonetheless, C2H6 should have a feature where you can see here that should be able to distinguish from other molecules. And the great one is propine. That's the C3H4. So it also has a distinct feature. But some caveats are some of the species are only measured at room temperature and at Earth condition with a 1 bar nitrogen background. These are all the gases with the label P and L. And the conditions are obviously different. For hydrogen and lower pressure, the transmission spectroscopy is probing. So we still need laboratory or calculation efforts to improve our opacity data.
Yeah, that's a great point. I see a question from Eric, I think, although, yeah, are you good to go?
Hi, Shami. It's Eric.
Hi,
Good to see you again. I think the last time I saw you, we were also talking about K218.
Eric.
So it's good to see this work. It's very interesting. I'll look at the preprint. A question about the hysteresis and cloud formation. How sensitive is that to the overturn time scale that you assumed, and where does your 1 month time scale come from?
Yeah, that's a good point. So I didn't actually model the dynamical temporal evolution of an eccentric system. So here I'm showing the steady state for radiative convective equilibrium of our climate calculations in 1D. And the question about how sensitive about refilling water above the cold trap depending on the vertical mixing. So as I remember, you would need very strong vertical mixing to have time scale shorter than about a month. I would argue it's possible, but it's less likely based on our knowledge of experience with the 3D climate modeling. Usually the vertical timescale inferred from at least from 3D climate modeling is providing timescale longer or roughly comparable to a month. Yeah, but there's an uncertainties there. It could be possible that if the planet has a very efficient vertical mixing, then the water could be refilled when the planet is moving out of the colder phases.
If I can just add one more sort of unrelated comment, the existence of a non-zero eccentricity, I think, might put a limit on the magma ocean scenario because that will also have a high dissipation.
What do you mean?
The eccentricity damping
Yeah.
so you presented 4 scenarios, and one of them includes Neptune-like atmosphere with a magma ocean.
Yes.
But the presence of a magma ocean will lower the Q, I think, I would assume.
Okay.
And that would basically, that might impact the timescale of circularization of the orbit, assuming there's nothing else exciting, which is the big assumption, right? In the system exciting the eccentricity. This could be forced, right?
Right. Yeah, that's a great point. Yeah, we didn't model this, but yeah, thanks for pointing that out. I guess it depends on the fraction of the melting upper mantle.
Yeah, I
Yeah,
don't think it takes much, but it'd be an interesting thing to investigate.
right. Yeah. But in
Great.
addition to that, I think what we can do is having a water survey so the water measurements for long period sub-Neptunes or Neptunian-like planets to see if water is somehow lower, due to the eccentricity effects. But I think, yeah, to your first comment, I think after this, I'll move away my obsession to K218b.
I see another hand up from Harrison.
Thanks, Anjali. Yeah, thanks for the great talk, Shami. You were saying about the sort of unknown vertical mixing to some extent in the context of this cloud feedback. Is this not something that we can get from looking at ratios in the chemistry though as well, if you're doing this chemical modeling at various different KCZs?
Yeah, definitely. So one thing I could think of is if it's a Sub-Neptune scenario, high KZZ should, high vertical mixing should make sure ammonia is transported to the observable region. So if it's a Sub-Neptune without a magma ocean surface to depleted nitrogen, and we can confirm observationally that ammonia is not present, that could probably place some upper limits about the vertical mixing. Yeah. Otherwise, I think in our study and also the recent paper by Renew Hu, I don't think the results are too sensitive to the vertical mixing.
Could appealing to like a different set of species also tell us? We'll see. There's ammonia, I guess, because of this thermochemical formation in the deeper atmosphere. But for example, could we look at like sulfur species or other molecules as well, and put together with multiple constraints, put together a picture about what's going on and learn a bit more about the mixing? Or is it just limited to mostly just ammonia and methane?
Yeah, potentially. Yeah. But in this study, we haven't done a thorough study exploring all different strengths of vertical mixing.
Okay, thanks.
Yeah. Thanks for the question.
Okay, so far I don't see any other hands raised. Last call for any other questions. Otherwise, if there are no more questions, I guess we can leave it there. Thank you again, Shami, for a very nice talk. And just a quick announcement for the Rocky World discussion for next month, which will be on the 4th of June. We will have Eleonora Allais from NASA Goddard talking about HWO and life, future space telescopes to look for life in the universe. So yeah, please do join us for that talk as well. Thank you again to Shami and for all your questions and discussion. And see you next month. Bye-bye.
Thank you, Anjali. Thank you all.